Welcome, everyone. So this session is about parallel computing in general. You might have seen that in the next sessions, there will be a session about parallel programming with MPI, with CUDA, with OpenMP and so on. And so the goal of this session is a bit to be an introduction to all those sessions and also to show you that you can start working in parallel on the cluster even if you do not know how to write parallel programs. So first, about the general concepts. When we talk about parallel programs, you will hear terms such as speed up, scale up, or scale out. So the speed up is to solve a problem faster by adding more processing power to it. Scale up is solving a larger problem by adding more processing power to it, and more memory and more network capacity. And scale out is solving many problems of the same size. In general, parallelization involves two things: a decomposition of the work, which can be distributing instruction to processors and distributing data to memories. And also, it involves the collaboration of the workers, so synchronization between the workers and communication of data. So these are the two main aspects of parallel computing. So decomposition can be decomposition of the work, and that will be called task-level parallelism. When you have a program that has to do two things that are completely independent one from another, you can work in a way that those two things are done in parallel. And you can decompose your data, and that will be called data-level parallelism. And there are several ways to decompose the data. If you have vectors in one dimension, you can decompose it by block or in a cyclic way. Also, if you have two dimensions, there are multiple ways to split the data and distribute it to the workers. Again, block, cyclic, or combination of both. Or you can have what we call a domain decomposition, where you will decompose the data in a way that makes sense with respect to the application domain of the data. About the collaboration, second aspect, we talk about the grain of the collaboration. So the fine grain parallelism is when your processors need to talk to each other very soon, very often, a large number of time per second. By contrast with the coarse grain parallelism is when the processors need to exchange data at a much lower rate. The other end of the spectrum here is called embarrassingly parallel. This is a class of problems that are just a collection of problems that are independent one from another and that can run entirely in parallel. And at the other end of the spectrum, we have synchronous computations, like SIMD is when exactly all the processors in the system, mostly on GPUs, for instance, do exactly the same computation at the same time, but on different parts of the data. When we talk about speed up, we also talk about efficiency and scalability. So the speed up is just a ratio between, so we talk about the speed up for P processors. The speed up is the ratio between the time it takes in series with only one processor divided by the time it takes with 10 processors. So if we have a task that takes 10 seconds, and if we are able to lower the time using 10 processors to 1 second, we have a speed up of 10. And the efficiency is the ratio between the speed up and the number of processors. So if we have 10 processors and a speed up of 10, we have an efficiency of 1. And this is the linear speed up that we represent here. Most of the time, this is what your speed up would look like. For smaller amounts of CPUs, could be potentially linear or perfect. but the more processors you add, the less likely you are to be on the perfect line. You could be in a negative speedup if for some reason you are trying to parallelize an algorithm that cannot inherently be parallelized with the overhead of parallelization you can have here. And sometimes you can also be super linear. And that happens when, by chance, the fact that you split the data into smaller chunks enables your data to be stored in faster memories. So it might be counterintuitive to say that, okay, if I multiply by 2 the number of processors, then the efficiency, the running time is divided maybe by 3 or 3.5. It can happen because of the layers of memories and the different speeds of the memories and their association and their sizes that could lead to a superlinear speedup. So the reason why your typical success sometimes is plateaued is most of the time due to what we call Amdahl's law. So when you have a problem, 100% of the time, there will be part of it that you can parallelize, and there will be a portion of it that you cannot parallelize. For instance, if you need to write a file and then compute some things, well, the reading of the file most of the time will not be parallelized. On some infrastructure with a parallel file system and a parallel library for reading file, it can happen, but just an example. And you see that if you have this part that cannot be parallelized and this part that can be parallelized, the more CPU or lines here you add, well, you can shrink this portion, but you will never be able to shrink this portion. So the law gives you the maximum speedup you can get as a portion of as a function of the number of the portion of the code that you can parallelize as a function of the number of CPUs. So you see that if you have a 95% of your code or running time that can be parallelized, there's no way in putting more than this amount of CPUs, and you will never get a better speedup than this. Okay, just because there's a part that you cannot parallelize. So that is one of the challenges. When you try to go parallel, you really need to be aware of the fact that not everything can be parallelized. Another, yes?
So it seems from this plot, for example, the green plot, I think it's like the best possible thing which you can get, and it looks like you should never use more than 2,000 processors. From the bottom is still.
Yes, when you get into this, well, first find the clusters with that amount of processor and getting access to it is a challenge in itself. But that being said, you never go to those lengths if you are not able to go to 99 or 95. Here, it's the running time. So the larger your data, the easier it is to get to high numbers in the terms of parallelization, because there's only the initialization that cannot be parallelized. And so most of the time you have a fixed cost for the initialization, and then you can spread out the cost of the parallel computing. The more data you have, the easier it is to actually parallelize in an efficient way.
But in principle, does it mean that in the future we don't need more than 2,000 processors now? There's no point in building such big machines?
I don't think so, because again, depending on the size, you could get much closer than 100 than this line here.
So you're saying that there are programs with 99%?
Yeah, and 6 nines. Mm-hmm. The program that runs for 10 days, maybe it's only 1 minute of non-parallelizable part. And so if you compare the two, you are much higher than, much closer than 100% than 95. But you really need large amount of data most of the time. But again, when you are running here, there are other challenges, because if you have that amount of CPUs, you know that within the 2 or 3 hours, there will be 1 or 2 nodes that crash, and you have to manage that. So the first challenge is a bit of a theoretical one. Second challenge is the overhead. So to be able to run in parallel, it means that you need to have a way for data to be transferred from one computer to another and so on. So there is a set of libraries or tools that you need to use to make that happen. And this is a code graph. So this is the set of functions that are called when you use the MPI library to simply have a hello world. So this is a hello world in parallel on multiple computers. So this is just the MPI overhead that sets up the environment to be able to talk to all the computers. And you will learn that in detail in the 2 MPI session next week. But in the end, it doesn't do anything much more than just printing hello world. But you see all the functions in the library that are called multiple times, and this induces a overhead, so that actually this simple hello world takes more time to run in parallel than it does in sequence. And if you are in the 1000 CPU, this can take minutes just to print hello world. Another challenge is the load imbalance. If you have data, you want to decompose the work. Sometimes it's trivial, it's easy. Sometimes it's not easy, especially if you are doing domain decomposition. If you remember the picture of the plane and the engine of the plane, it could be that some portion of the data takes much more time than others, which is illustrated here. So that several workers share the load, but in an imbalanced way, and that induces well, I mean, this one could end up not working for a certain amount of time. So it's a thing that you need to be aware of if you want to be able to extract the maximum power of the cluster. Okay, so these are just the large topic. Any question about that? No, it's basically things you need to be aware of. Now, I would like to show you a bit more the hardware. So the better you understand the hardware, the better you will be able to write and distribute the work correctly to write software. So you know that in a computer, there are cores. And inside the cores, so the compute unit in the CPU, there is already a way for working in parallel. So this is the block diagram of a typical core. And you see there are multiple ports. And actually, there are multiple portions of the core that are able to do computations, and they can do it in parallel. It's something you should not be afraid of, because it's the compiler who will organize the work for this, both the compiler and the CPU itself with the scheduler here. So within one compute unit on a computer, you already have a scheduler that will distribute the work around across multiple compute units. But this you don't need to think about. It's both the job of the CPU and the compiler. But you know that the cores in a CPU, you can have multiple. I'm sure on your laptop, you have 4 cores. 1, 2, 3, 4. This is a graphical representation of a chip. So the CPU that you can have in your laptop. You see that there is a memory here, another type of memory controller. So that links to the memory DIMMs on the motherboard. And you see here, for example, 4 cores, but on the clusters, you can have up to 64 cores in the same DIMMs, in the same physical CPU. And then you can have multiple CPUs on the same machine. So typically, the machines that we have, the servers that we have in the clusters, they have either 2 or 4 CPUs. And each CPU can have multiple cores. So in one computer, you can have 256, for instance, CPUs or cores. at the same time in the same machine. And then on the cluster, some nodes, we have accelerators. So additional equipment with additional computing power in the form of typically GPUs, so graphical processing units. So nearly the same GPUs that you have in your playing machine or gaming machine at home, but here we use them for computations. And then if you stack all those compute nodes into racks, you get a data center. And in the data center, you can connect all those compute nodes with a very fast network, and you get what we call a cluster. So you know that at CC, we offer access to clusters. They are distributed on the 5 universities that are a member of the consortium. So basically a set of machines into racks with a very fast network. The same definition applies to clouds. If you've heard about cloud computing, it's exactly the same, computers in racks with a very fast network. But the difference is in the way you use the machines. So the cluster has a scheduler, you connect with SSH, and then you submit jobs. And the cloud is different. You connect to a web interface, and you spawn virtual machines on the cluster, on the cloud, and then you do whatever you want with the virtual machines. So these are the two type of platforms you could face when you try to do parallel computing. We do not have any cloud available for the users at the CC. Just some universities we have an OpenStack for some services. But the next version of Vega will have an infrastructure which is very much more similar to a cloud than to an actual cluster. And then if you combine multiple clusters into one, you end up with a grid, such as the grid of the WLCG, so the Worldwide LHC Computing Grid. So it's a set of clusters across the world who process the data from the large collider at CERN. Another way to collect data, to collect computing power from across the world is with distributed computing. Maybe you've heard about City at Home. It's a very old project where you can actually donate some computing time of your laptop to the project so that they analyze signals from outer space to try to find life over there. And this is called distributed computing. So you see that parallelism can be thought of at the world level, such as like this, or at the nanometer level in the microchip with what I showed in the very first slide. And you will need to find your sweet spot into this spectrum. So I'm just talking a little bit about the programming models, because as I said earlier, it's the topic of at least 5 sessions to come, just to set the big picture. So about the paradigm, so how is work organized? There are 5 or 6 typical ways to organize work. One is task farming, where you have no communication between the workers. You can have 2 variants. One where there's a master that distributes the work to the workers. We call it now leader follower or master slave. And there's another variant where the workers actually pick from a pool of work some work to do, and that is called work stealing. You have what we call single program multiple data, where the idea is you write some software that is unique, so single program, and that will be spawned multiple times to manage multiple parts of the data. So the idea here is the one that will be implemented in the MPI libraries or the OpenMP work. So you will see that in detail in the MPI and OpenMP like training session. Multiple MPMD, multiple programs, multiple data is just an extension of this, but this is the most common type of parallel program. These are other types of parallel programming. Pipelining is when you work like in a plant. So you have multiple processors that take part of a portion of the whole process. Divide and conquer is not much used in the HPC, but much more used in big data. If you know about Hadoop, Spark, this is the spirit where processes are spawned at need and then they merge the result back to the parent. And then there's also the final here, which I mentioned just for the sake of completeness, is speculative parallelism. The idea is that when you have an if condition in a piece of code and that the evaluation of the condition takes a lot of time, what you can do is spawn two processes, two programs, one which will do the part if the condition is true, and the other one which will do the part if the condition is false. And then when you get the result of the evaluation of the condition, you just discard the branch that does not correspond to the reality. So this is a way to avoid being blocked as a branch point in your code if the evaluation of the condition is time consuming. So on a single computer, I said you have multiple CPUs, and so the tools or the libraries or syntax constructs that you can use are pthreads, OpenMP, thread building blocks, and OpenCL. So we have a session about OpenMP, and that's it. For accelerators, so GPUs, you have multiple paradigms you can use, and we have both a session about CUDA, which will be given by Olivier, and a session about OpenSCC and OpenMP given by Ola. And then on multiple computers, depending on the fact that the memory is shared or distributed, you have, when you have a shared storage, you have MPI on the clusters. This is the most important libraries that we install on the clusters. It really is the one that enables you to create a parallel program. So we have two sessions about MPI. If you have distributed storage, this is much more the application on the clouds with MapReduce and all the most modern versions. And if you have no storage, you have Boeing, and this is the tools that is used in distributed computing, such as I mentioned earlier, Setieto or Foldaton. And then you have tools such as coarrays in Fortran and UPC in C that allow you actually to see a set of computers as if it were a single machine with a unified memory. So with MPI, you will see that it's a distributed memory. So you will have to think about data movement from one memory, from a server to another server, and you will have to manage those memory movements. With these coarrays or UPC, you don't have to think about that, but it induces, again, an overhead, because behind the scenes, it has to do a lot of synchronizations and so on. It's easier to write programs with this, but it's easier to write slow programs with this. If you really want to perform, most of the time, you will have to manage the memory by yourself. So I will not go further into details about these, because as I said multiple times already, there will be sessions about that later. Rather, I will focus on user tools that GNU Linux already offers. So maybe you attended the session by Bernard, who gave you the basics of Linux and the command line. And here I will show you tools in the command line that enable you already to work in parallel. So for that, I will show example based on a silly program written in Bash that does nothing except it's called lower.sh. And you can either give it a file or feed data through the standard input to it. And what it does, it takes character by character and it sets it in lowercase. And it sleeps for 1 second just to do as if it was a CPU intensive program. Okay, so what you see here is just a read loop. It sleeps, it takes what is as read and put it in the uppercase. And here, if you specify an output file, it will write it to the output file. Otherwise, it will write it to std out. And so I have in the directory a few files which contain some characters here. And so in the next few slides, I will show you runs of that program on that file. And you see if I apply the program on the file, here you have uppercase letters and you have here the result, which is the corresponding lowercase letters. Okay, you understand the setup? Okay, it's easy just for the illustration. So the first thing to know is that in Bash, you can separate commands with a semicolon. So here, this semicolon just means that I'm running lower on this file and I wanted to create this file. And then afterwards, I want to run lower on this file and create this file. And this really means afterwards. So first do this and then do this. I will add a few elements to the line here. And this is the time command in Bash, which is used to measure how much time some command takes to run. So the idea is that I will compute the time it takes to do this and then this, okay? If you understand the thing, you should already anticipate the fact that it takes 8 seconds. So this is an 8. So because this takes 4 seconds and this also 4 seconds, because there are 4 lines in this file and we have a processing that takes 1 second per line. Okay, you understand this? No, you will see a small change. I will replace the semicolon here with an ampersand. And I will also set an ampersand here. And I will add the wait bash command. And this will actually lead to those 2 commands being run in parallel. From Bash's point of view, Bash will start this and then immediately start this and then immediately start this, but this is a wait that will wait until this and this has finished. So again, if I use time to measure all this, it takes only 4 seconds, just to illustrate the fact that because I ended both my computations with the ampersand, they were put, as we call it, in the background, and the second one started not waiting for the first one to be finished. So this is the simplest form of running in parallel on Bash. Just running multiple programs and ending them with an ampersand to put them in the background. So, first thing I want to show is when you have one program and many files. So we are in the context of embarrassingly parallel computing, if you remember the concepts from earlier slides. So here, what I show you is that I have 4 files in my directory named D1, D2 until D4. And I'm using the xargs command from Bash. I don't know if you know it, but basically what it does, it takes something from the standard input and then give it as argument to the command that we give it as argument. So if I use ls and then this pattern matching to list 4 files, and I use xargs and then echo file colon, then I have this echo command run 4 times, once per file. Okay, I don't know if you knew the xargs command already, or I can go further. Okay, so you understand the idea. So what is before the pipe is given as argument to the command that is itself given as argument to xargs. So why do I speak about xargs? It's because it has a nice argument here. And to show you what it's used for, I will use again my lower example. So here, I use the same constructs as here, but here rather than having echo, I use lower.sh. So what this will do, it will take all 4 files and feed them to the lower.sh file program, thanks to the xargs argument here. Okay, so this will take 16 seconds. Why? Because we have 4 files. In each file, you saw that we have 4 lines, and each line takes 1 second to be processed. We understand each other. The nice thing is, if I add 1 parameter to xargs, which is capital P4, I'm actually instructing xargs to do the same work, but using 4 processes. So if I have 4 processors available, they will be dispatched on the 4 processors. And the time it takes is shrink back to 4 seconds, which is the time it takes for 1 run of the lower.sh program to run. Okay? So it's a bit of a cheat here because the sleep command can be parallelized very easily, but the idea works even with CPU intensive work, as long as you have enough cores that you give to the system. And basically, xargs with -P is equivalent to running all this. Difference is that you only use 1 line to express the 5 lines here.
So what do you need this arrow there now?
So here, why there's a redirection, because I'm not interested in the result itself, rather in the time it takes. And the output of this is 16 lines with A, C, D, G, and so forth. And I don't want to show them. So I redirect the output to /dev_null, which is a special file in Linux that eats everything you get to it. So basically, I'm suppressing the output of this.
And another question. So you specify P equal 4. What happens if you specify P equal 3, for example?
So if here I specify P equal to 3, I will have 8 seconds here. Because 3 will run in parallel, and then the last one will run after it. So it will take 4 seconds to run the first 3 ones, and then 4 seconds to run the last one. So the total would be 8.
And so it is the operating system that parallelizes it, right? So when you use ampersand or?
Yes, so the thing is that this construct will create processes, and the operating system will take all the processes and dispatch them to the processors it has available.
And so it works on if we have 4 cores, right? For example, if I have 4 cores, but I want to parallelize 8 jobs at the same time, will it work?
It will work in the sense that it will not crash, but it will not work in the sense that it will take twice the amount of time compared to if you had 8 cores available.
So basically, this P should be equal to the number of cores. Also. Right?
If this operation is CPU bound, as we say, so if it takes a lot of CPU, yes, you should match this number with the number of cores you requested in the cluster. Okay, so this is when you have 1 program and many files. But sometimes it's the opposite. You have multiple programs and 1 file. So here I'm showing you the opposite of lower. So if you remember, lower would take uppercase letters and transform them to lowercase, but upper does exactly the same thing in the other direction. Okay, so here again, I'm running lower on this file and create this file, then semicolon, so I'm waiting, and then running upper on the file that is the output of the previous command. So this is an important point, and to create a file which is rest.txt. Okay, so if I run this, it will first run this to produce that, and run this to produce that. So one file, 4 lines, 1 second per line. It's 4 seconds here, and the same here, so it's 8 seconds here. Okay, so this is not parallel. The trick here is that because lower and upper, I said earlier, are able to ingest data from standard input and produce data on standard output, you can chain them with a pipe. And doing that, actually, this will start as soon as the first line is written here. So it will not wait until this one has finished to start. So the total running time is 5 seconds. Okay, so the first second, this one will process the first line. At second 2, it will give the first line to this file and process the second line. And this will take 1 second to process. So the total time will be 5 seconds instead of 8 seconds. We have 1 second additional because this one cannot start before this one has finished at least 1 iteration. But you see that it's working in parallel in a pipeline way. If you remember the notion of pipeline, I talked a bit about earlier. So it's very important to know that the pipe is able to create processes that will work in parallel, and the second one will eat what the first one is producing as soon as it is available. Mm-hmm.
So what happens if in upper we read more frequently? For example, we read 1 second or half of a second. So first it waits 1 second until lower writes the first line, then it reads it, and then will it wait or?
So if the rate is not the same here and here, if this one is faster than this one, the data will be accumulated by the operating system into a buffer, a temporary buffer. So if the rate is too different, you might overeat all the memory of the node. Okay, but there is a buffer hidden here in the implementation.
But what happens
in
the other way?
In the other way, if this one is faster than this one, it just switches. So you really need to see this as a pipe. And this is putting something at the beginning, and this one is waiting for stuff to come at the.
But it waits during the read instruction, right?
Yes. Another question you might have is, what if my program is not able to use standard input and standard outputs? Because I showed you how it works with the pipe, which connects the STD out from one program to STD in of another program. Well, there's a solution too. It's called a FIFO. It's a special type of file called a first in, first out, which you can create in your file system. And the thing is that if you write into this file, another program can read from this file, and it will be functionally exactly equivalent to using the pipe with STD in and STD out. So with the same issues if one is slower than the other and so on. But this is a way to get this type of parallelization, even if your program is only able to read and create and write files and not able to use a standard input and standard output. This is what I just said. Okay, so this was with several programs in one file. Now we can have another type of processing, which is one program and one very large file. rather than having multiple files, you have one file with a large content, and you want to be able to work it in parallel. For that, there is a command called split in bash, which will split a large file into different portions, and you decide how it is split. By default, it will split on the lines. And you see that it accepts a filter option where you give it the name of some program. And what this does, it takes this file, split it in this number, which means round robin over 4. So the first line is given to processor 1, the second line to processor 2, third line to 3, fourth line to 4, fifth line to first, and so on. And if you do that, you see that the running time has shrunk to 1 second. Even though there are 4 lines in the file, and you know that it takes 1 second to process 1 line, this split with filter will actually create 4 instances of this program and feed each instance with a portion of the file. So this is the same line as here, but I show you with top that there are actually 4 instances of the program running at the same time, and each processing a line of the file so that it takes only 1 second in the end. So split is a nice tool to split a file and process parts of the file in parallel independently. So this is again split. So 1 second instead of this slide should be actually before. And then, so we've seen one program and many files. We've seen many files, many programs in one file. We've seen one large file in one program. And we can have also the case where we have multiple programs and multiple files. And for that, you can use a makefile. So maybe you know about makefiles because when you want to compile code by yourself, most of the time you will download an archive or clone a Git repository, and then you will see that instructions say, okay, configure, make install, for instance. So the makefile was created at the beginning to build software, but it can be used for other things. And so here, I'm showing you an example of makefile where I talk about 4 files, which I call D1 to D4.res. This will be the result files that I want to produce. And then in the makefile, I give you, I set the rules that say how we go from, how we produce .res, for instance. To produce a .res file, it's written here. I use a .tmp and I run this program using this as input and this as output. This is what those ugly characters mean. But then the question is, how do you produce the .tmp file? Well, the rule is here. To produce the .tmp file, you use the .txt file and you run lower with the same kind of stuff. Okay, so this makefile says that to produce the result file, or 4 of them, I need to first run lower and then, I first need to run lower on each of them and then upper on each of them. If I do that and I compute the time, you see everything it does. So we have 8 lines, 4 seconds per line, so the total is 32 seconds. Okay, so what is expected? But again, just like xargs, there's a nice parameter called -j, where you can specify a number of processors. So if I run exactly the same make command, it does exactly the same thing, but it only takes 8 seconds. Why? Because every line here does not depend on anything else, so that they can be run in parallel. So it takes exactly the same time as one instance, which is 4 seconds. And then this one all have to wait on the result of this one, but it's only 4 seconds, and then they run for 4 seconds. So the total time is 8 seconds. Okay, so this is a proof that using the -j, you are actually able to produce a makefile that runs in parallel. So if you have multiple steps in your workflow, basically, if you are able to encode the dependencies in input and output of each of the steps into a makefile, then you get the parallelization for free just by using the -j operator from make.
Yes, but yes. Are we obliged to specify we want to split it in 4? Or this argument, is it mandatory or optional?
So this argument is, so it's not mandatory, it's optional. But if you don't, I don't remember, if you don't specify it, it's sequential. If you don't specify the number here, it will use all CPUs that it finds on the compute node. And if you specify it, then you can specify exactly the number. And the same discussion as before with xargs applies here. If you put here a number larger than the number of CPUs, and these are CPU intensive, then you will be suboptimal. And if you put here a number lower than the number of CPU, then you will have 1 or 2 CPUs not doing anything. So it's always best to fit this number with the actual number of CPUs you request.
For example, if I'm compiling something on the cluster and I don't exactly know how much CPU I have and in how much part it will need to split.
If you're using make for compiling a program which was given to you, and you are doing it on the front node without submitting a job, then a good rule of thumb is put 8 or 4 here.
Okay.
More than that, you might run into issues in make where the dependencies are not quite involved. So at the beginning, when we first had the nodes with 64 cores, we have seen make completely fail at handling the dependencies on order for the 64 cores. And the thing is that between 4 and 8, for compiling, you will use maybe 2 to 6 CPUs because the making process involves a lot of disk access. So it's not CPU intensive. And so if you go, if you are between 4 and 8, it should be the sweet point. The sweet point, yeah, good value. Okay, so in summary, it's not necessary to build a parallel program to be able to process your data in parallel on the clusters. What you need to know are the 4 or 5 keywords in bash here. So if you have a very large file to process with one program, you can use split. If you have multiple programs, you can use pipes or FIFO if your program is not able to use pipes. If you have many files to process, you can use xargs or make if you have many programs. And actually, if you have many large files to process, you can mix all the solutions together. So all of this was simply using the basic functionalities of bash. So the basic shell that is installed on the cluster. But we can go a step further by using a program called the GNU Parallel. So this program was actually designed to do everything that we talked about here in a single program. I'm going to show you a few examples here because the syntax is pretty nice. So I'm running parallel and then the echo command, which is like print in bash, I'm sure you know about it. And then you see 3 columns here and then 1, 2, 3, 4. And what this does, it takes all elements in the list here and gives it as argument to this command. So I have here a 1, 2, 3, 4, and this happens in parallel. This is another way to write 1 to 10, but this is pure bash. Has nothing to do with GNU Parallel, just to show you for the examples afterwards. This with time to show you that it's in parallel. So I have a sleep command that will run 10 times with argument 1 to 10. And so the total times is here 11 seconds. So actually, as they run in parallel, the optimal time should be 10 seconds. But the fact that we use GNU Parallel, it also takes time to start to set up the environment. So there is some overhead, which is illustrated here in the additional second. Here, again, this is bash for pattern matching what the character and then the txt. So if I run parallel echo, I have all these files. Okay, just to show you how it works, because you can do interesting things with GNU Parallel. Here you have the same as before, except that I'm using curly braces here. And the curly braces is a placeholder for the elements that are here. So remember that this expands to d1 to d4.txt, and it will be placed here. And here, it's a way that GNU Parallel allows you to modify the placeholder. So if I run echo, this will be exactly this, and this will be this, where the extension is replaced by this. And so with this line, actually, it will output this. So you see d1.txt and then d1.res. Why? Because it took d1, 2, 3, 4, put it here, and then remove the extension and add the res, and you have this. So this is a nice way for you to generate all the commands that are necessary if you have multiple files that you need to process and rename to something else. And name the result as a function of the input file. Also, you can use this type of construct to extract the portion of the path, which is the file name compared with the DNU, the directory. So Parallel allows you to create processes in parallel, and it has a very specific syntax to play with the arguments that is provided. You can provide multiple arguments. So here I provide 1, 2, 3, 4, and AB, and what it will do is just a product of those. So we have all pairwise combinations created for you. So if you have parameter sweeps that you want to perform with one program, 2 parameters, and you want to test all possibilities of the parameters, you can do it in the line with parallel. You put here parallel, your program, and then the first set of parameter values and the second set of parameter values, and it will test all possibilities. If rather you want this one with this one and this one with this one, you just use --xapply. So it's also a nice way to generate the command lines that you would run, but in a single line. And again, using the placeholders, you can refer to the first element or the second element. And here I use parallel echo 1 and 2. So this will be replaced by this, and this, and this, and this, and this by this, and all the different possibilities. If you don't need all the product of the arguments, you can use a file. So here, assume that I have a file called experiments.csv that has 2 columns, one named number, the other named letter, and I have 1A, 2B, 3B, anything that I need to test, for instance, if there were parameters in the function. And then I can use parallel, and you see here I have 4 columns rather than 3, which means that this is a file where the parameters can be found rather than the parameter itself. And then I can refer to the column numbers, to the columns by their names in the command here. So I run parallel, I specify the column separator, which is a comma. I specify the header, which ends at the first character return, new line. And then I use echo number letter. So it corresponds to first column, second column, and it just echoes the first column and the second column. Okay, so typically, if you have a program and you want to test multiple combinations, but not all of them, you can list them in a file and then use Parallel to run all the different options in parallel. GNU Parallel also has a /5 option to split a file, just like when we use the split command. We can specify remote servers with -S, capital S. So if you are using your laptop and your workstation and you're working not on a cluster, but on your laptop, you can use this to say, okay, run on my laptop, but also on the workstation. And GNU Parallel will distribute the work. It will copy the data that needs to be copied, as long as you have SSH access to the other node. You can specify the maximum number of jobs to run in parallel, just like the capital P in xargs or the -J in make. And the same discussion applies with respect to number of cores you have and the fact that the program is CPU bound or not. And this is a very nice thing, is a keep same order. In many of the options I've talked earlier, the fact that it runs in parallel sometimes can induce a change in the order of the output compared with the order of the input. Sometimes it doesn't matter because you are averaging the results, for instance, and the order in the sum does not is not important, but sometimes it's important. And with GNU Parallel, you can say to GNU Parallel, okay, please keep the order in the output. So it means that it could be a bit slower than if you don't care about the output, because it could be that as long as the second result is not available, you will not see the other results afterwards. And then you can set up a delay and a timeout if you want to not all the tasks to start at the same moment for some reason. If you have many tasks that all need to read the same file, you don't want them to do that at the same time. And you can specify a timeout to say, okay, if task is taking more than X, then I want it to be kept. If you are using that program in a publication or work, you're supposed to include this citation to acknowledge the fact that you're using the GNU Parallel software. Yeah, so Olivier mentioned in the chat that on most clusters, the parallel command that you get without loading any module is often, if it exists, is an old version. And so the best option is always to use module load parallel to get access to the most recent version of GNU Parallel that is available on the cluster. Okay, it's 5 o'clock. It's about everything I wanted to say for this session. So if you are still having a bit of energy, what you can try to do is reproduce all the examples with upper and lower that I showed, but using GNU Parallel. So I said that GNU Parallel is able to do anything that xargs, make, and so on can do. So you can try to do it. And if you are too tired, the solution is here. And actually, the multiple programs and multiple files is longer. It's working. Do you have any questions about this? It was a short session, just to set up the ideas before we get the parallel programming session next week, and to show you that you can still start working in parallel without writing parallel programs.